6.5, measuring the change in internal energy for chemical reactions. So we've talked about how systems and surroundings exchange energy. They exchange energy by the means of heat and pressure volume work. So we've got the system and the surroundings. There can be an exchange of energy because of a difference in temperature, a heat transfer, or there can be work that's done either by the surroundings or by the system. So when we talk about delta E, the change in internal energy, that's a measure of all the energy exchanged between the system and the surroundings. It's going to be heat and work. So delta E equals Q plus W. Well, if there's no change in volume, do you remember what the equation for that pressure volume work was? W equals what? Negative P times the change in volume. So if the volume change is 0, then the work done is 0. And we get the change in energy is equal to Q. It's just the heat. That's at constant volume. So the Q with a subscript V here is telling us heat exchanged at constant volume. So that's the change in energy for the reaction. We can't look at temperature changes of individual reactants in a reaction because they're too small. You can't measure that. But you can look at the temperature of the entire solution, and you can look at how it interacts with the surroundings. And so we measure the temperature change in the surroundings using a controlled surrounding. And it's called a bomb calorimeter. So we define the system as the system is the chemical reaction. The surroundings would be the bomb calorimeter. And so the energy lost by the system is equal to the energy gained by the surroundings or vice versa. And this will be the heat gained by that calorimeter. Calorimetry, so that's a combination of two words, calorie and metry or metric, measuring. So measuring calories. It's a technique where we measure the heat of a reaction by observing changes in temperatures of the surroundings. So you've got the reaction that is our system, and it's exchanging heat with the surroundings. We control that as a calorimeter where we can measure the change in temperature. So this is a picture of a bomb calorimeter. It's kind of fancy. I'm not sure why they call it a bomb calorimeter, except maybe it looks like a bomb. I don't know. This is the bomb part. And so here's this tightly sealed container, and we've got the sample inside, and they put oxygen. So you can put a sample in here, and this is the sort of apparatus they would use to determine the calorie content of, say, foods. They burn it with oxygen, and they measure the heat given off. So we've got this container in here. All the heat that's given off here is going to be absorbed by the water in this external containment part. Okay? There's a stirrer here to mix the water so that the heat given off by the little bomb is uniformly distributed. We've got a thermometer here, and this is all sealed up and insulated so that it's not losing any heat to the rest of the universe. There's ignition wires here, and so what they do is they get this going with a spark, and they burn it, and they measure the change in temperature of the water around it. So the calorimeter constant is the heat capacity of the calorimeter. So remember, there was heat capacity and there was specific heat capacity. Specific heat capacity was like joules per gram degree Celsius. The heat capacity was just joules per degree Celsius. And so because this bomb calorimeter's mass is always the same, we don't worry about having a specific heat capacity for it. We just look at the heat capacity. So Q, the heat absorbed by the calorimeter, equals the calorimeter constant times its change in temperature. That is equal but opposite in sign to the heat given off by the reaction. Q of the reaction is heat at constant volume, which is equal to the change in energy for the reaction. Any questions? Maybe why? Let's do a problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find the change in energy for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, which was determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So there's our bomb calorimeter. There's water in here. And let's do orange maybe. Inside the bomb, we have 1.550 grams of liquid hexane that's combusting, it's burning. It's going to release heat when it does that. We could write the chemical equation, but we don't need it, so we're not going to. When this burns, giving off heat, the heat is absorbed by the water in the calorimeter and the temperature changes. So the initial temperature of the calorimeter is what? 25.87 degrees Celsius. And the final temperature is given as 38.13 degrees Celsius. So we can calculate the change in temperature. It's the final minus the initial. 38.13 minus 25.87. So the temperature rose 12.26 degrees Celsius. You with me? Why did the water get warmer? It absorbed energy from the reaction. We have an equation for that, right? So Q for the calorimeter is equal to the calorimeter constant times the change in temperature. We measure the change in temperature. In a separate experiment, we determined the calorimeter constant. So we can calculate how much energy in joules or kilojoules was absorbed by the calorimeter. Does that make sense? So the energy absorbed by the calorimeter equals the calorimeter constant, 5.73 kilojoules per degree Celsius, times the change in temperature, which we just calculated as 12.26 degrees Celsius. So that equals 70.24. Let's see, we should have 3 sig figs. So 24, I don't want to mess around. 2498. What's the unit on that? Kilojoules. So the degrees Celsius cancel out. That was the amount of heat absorbed by the water. What was the heat given off by the reaction? It's the same number, right? What we're trying to find is delta E for the reaction, but they're specifying these units, kilojoules per mole of hexane. Q for the reaction equals minus Q for the calorimeter. So the reaction released 70.2498 kilojoules. Was that released by 1 mole of hexane? No. It was released by 1.550 grams of hexane reacting. If we want units of kilojoules per mole, how could we get those units? We could take the amount of energy in kilojoules and divide it by the number of moles that created that. There's not an equation for this. You just kind of have to think it through. Well, we need the molar mass then of hexane, don't we? 6 times 12.01 plus 14 times 1.008. 6 times 12.01 plus 14 times 1.008 equals 86.172 grams per mole. So we could take this 1.550 grams of hexane and use the molar mass we just calculated to figure out how many moles that is. .550 divided by 86.172. 0.017998. I'm counting sig figs. There should be 4 sig figs. 73 moles. So this much energy was released, 70.2, for this many moles. Well, I need some space. Let's erase this title up here. We don't need that. So delta E for this reaction is equal to Q for the reaction because this is happening at constant volume. The volume is not being allowed to change, so there's no work being done. So I've got this negative 70.2498 kilojoules. I'm going to divide by the number of moles. I should have 3 sig figs on this. 3905.5 kilojoules per mole. How would I round that? It would be 3,910 kilojoules per mole. What happens a lot is students will say it's 391, but that's changing the number. So put it in scientific notation and then round it. So scientific notation, I'm going to put the decimal point after the 3. So I'm going to get negative 3 point, and I'm going to keep the 9 and round the 0 up to a 1. And then I've got times 10 to the, I moved it 3 places, and my units are kilojoules per mole. Usually when we're writing delta E reaction, we're going to include the negative sign because that tells us this is an exothermic reaction. When hexane burns, it releases energy. If the question is asked, how much energy per mole is released, then we would express it as a positive number because the words tell us the direction. Any questions? For in this exercise, they're saying find delta E. So then we should include the sign, because find delta E is not telling us what direction the energy flow is. If it asked, find how much energy in kilojoules per mole is released, then you would leave the negative off. I know that's confusing.
Yeah, final question. You didn't get it. Why don't we include the mass in the Q calorimeter?
Why don't we include the mass? Okay, this is a heat capacity, not a specific heat capacity. So there's no gram term down here. This would be different for every calorimeter, but it's constant for this one particular calorimeter. So we call it the calorimeter constant. It's a heat capacity, not a specific heat capacity. Any other questions?